of Tom Haskins working on his PhD thesis. And yeah, before I give the floor to Errol, I hope that people will join for the drinks that we have after this, after the colloquium. For people who gave their address, you received hopefully a package with some goodies, and with, of course, everybody is very much welcome to join in the Garda town. I will paste the link again in the chat. But before we start off with a bowl with the drinks, the floor is completely yours, Errol.
Okay, so let me.
I propose that if there is questions that we use the chat, and I can try to answer them while Errol is talking. And else we wait until the end.
Okay, you have a distributed workflow, Hans.
No, but I think that anybody who can. I mean, we do that a lot. That we chat,
Okay.
but don't interrupt the speaker, but just use the chat, and then in the end we can always look for the interesting questions.
Yeah, let's do that. That's a good mode of working.
Control L for that. You see my share the document?
Yes.
Yes.
The mouse is not coming up, but Control L is the laser, right?
Normally it is.
But then you have to go to the right screen with your mouse to do a page down, I think. Let's see.
Okay, wait a minute. And then. So you see it changing?
Yes.
Yes. Yes.
Yeah. The laser is not coming up, by the way, so that's
okay.
But it's okay, yeah?
Yeah.
Okay, let's start off. Thank you for having me. Today we're gonna, in this presentation, want to discuss the merits and challenges of causal inference using data within the ASML context. We're gonna starting off with an introduction to ASML, and then the diagnostic challenges we face, an approach of causality from data with focus on transfer entropy, and then discuss some cases, including one ASML case. Regrettably, I have to take one out, but never mind. I have a very interesting replacement for this case, and then we of course will conclude with some conclusions and open research questions. ASML is a prominent supplier of lithography systems that the semiconductor industry use to produce ICs, the core units in our electronic devices that makes our life looks somewhat easier. For some people, it does make life more easy. But anyway, ASML has global prominence, global presence, located in 16 countries in 60 offices. And I think we have about 25,000 employees, most of which are based in Europe, headquartered, of course, in Veldhoven, and the rest of the people are based in America, 6,000, I guess, more or less, and then 6,000 in Asia. So quite a big company with a lot of people doing wonderful things. So like I just mentioned, ASML manufactures lithography systems. These systems are really complex. It's a Champions League in engineering, I would say. Optics, vacuum technology, plasma physics, accuracies to be reached, like on a nanometer scale and millikelvin, thousands of sensors to observe the physical behavior of the system, and then sampling rates that range from kilohertz, let's say 50 kilohertz, to 1 or twice a day. So very challenging. So one can imagine that diagnosing such a system is very challenging. Currently, ASML is mainly relies on historic data and physics-based models. Historic data is used to apply pattern matching and rule creation to diagnose the everyday issues or failures, let's say the high frequency failures. But we also use design knowledge to identify failure modes in an early stage. And it's also very, very interesting with working with some parties on that. And lastly, we use a digital twin approach to use real data to feed a simulation model to simulate the behavior of real systems. So again, we mainly rely on historic data and on models. However, modeling is as you can imagine, challenging by the growing system complexity. We have to deal with high dimensionality, with nonlinear interactions, with non-stationarity of processes in the system. And we also have to deal with the things that we don't observe because we cannot observe them, or we don't know that we have to observe them. But in the meantime, these non-observables have a great impact on the things that we do observe. So there's a real challenge there. So this presentation will discuss an alternative data-driven approach to get around these challenges that I just mentioned. So what's what kind of data do we generate on a daily basis? We have event logs coming from the source and the scanner systems, BORDIMS, all kind of tracings. We have performance data like throughput, latency, queue sizes, amongst others. The volume is very high. For high-end systems, we're talking about 1 gig per wafer, and such a system produces like more than 200 wafers a day, an hour. So a lot of data there, and the number of parameters is 100,000. So quite a lot. So processing all this data is quite a challenge. I just mentioned the wide range of sampling rates, ranging from 50 kilohertz to 1 or twice a day. I know an observation a week. So that's amazing, giving us a hard time to fill in the gaps. So if you take these signals together, the fast one and the slower ones, then you automatically get gaps for free. And how to fill them up? That's a real challenge. And we also deal with poor data quality, missing data, outliers, noise, and sometimes also non-uniformly sampled data. So the distance between subsequent data points is not equidistant. Well, the main focus we have, so the toughest problems we face are unknown and rare system failures. I just mentioned that for the common issues, we have pattern matching and rules in place. But for the unknown and the rare system failures, we simply have nothing. We don't have the historic experience. We don't have the historic data. So we don't have the statistics, if you will. System performance degradation, that's another thing that we focus on. While the machine is running, it's getting dirty, and so we have the reflectivity going down slowly. And so that's a very challenging problem. And trying to solve all these problems, we want the solution, of course, as fast as possible. And our dream is to have a diagnostic application that works as fast as is as near as real time, which is quite a challenge, of course. We now set up a line of research or investigating an information theory-based approach. Why? Because we have a lot of all this data that I just mentioned. We have information theory-based approaches doesn't require any predefined models, by which I mean that you can capture a wide range of relations without a prior assumption on interactions. So that's, of course, very nice, because the system is linear in its behavior, but it's also nonlinear in its behavior. So it's then very nice if you don't have to predefine the nature of the interactions. And another advantage, of course, is that once you have this, you can create a graph, a network, a causal network, and once you have that, you can, including non-obvious links, by the way, so which allows to do real causal discovery, because things that cannot be predicted by the model, because models do not, by nature, do not predict abnormal behavior, you can capture from the data, creating these causal graphs and find non-obvious links, so to speak. And lastly, once you have this graph, it allows you to use other techniques, other measures than information theoretical ones. And I'm a fan of graph-based measures. And I specifically mention here spectral centrality, because that's the measure used so far that I have that looks very promising, because it's able to so once you reconstruct a causal graph, you can order your variables based on their influence on the rest of the network. But we will come to that later. So notions of causality. I felt here that I have to say something about causality, because it is a subject, it's still under debate for quite some time. I think it goes before the time of Immanuel Kant. So we're talking about a debate that is more than 50 years old. And I have the feeling that it might go on for another 50 years. So there are two pioneers in this that we can link to this study of causality, namely Judea Pearl, who states that if I change x, to what degree does y change? and he calls that interventional causality. And then we have Norbert Wiener, who state, if I know state X, to what degree does that help to predict Y? And he calls that observational causality. I don't have to tell you that it's more like a statistical notion of causality. As we at ASML, since we make machines, we decided to stick with Mr. Wiener because his notion of causality is a working definition, and it seems to work. So we can start investigating his let's say the implementation of his notion, which is transfer entropy. So we focus on observation-based methods, and I hope this will help to get you to the introduction of transfer entropy and later on eigencentrality for ordering. But I have to mention there is one more measure that my dear colleague David Zichtermans worked on, and he called it causal tensors. I'm not going into details about that. He have some publications, I think 3 or so on this. So I included a reference of his work at the end of this presentation for those who are interested. But now I'm going to focus on transfer entropy. Okay, transfer entropy, I just mentioned it. Transfer entropy is a Wiener implementation of causality. So it's about prediction. So if I know the state of X, to what degree is that going to help me to predict the future of Y? In this case, so here's a case with 2 time series, X and Y. I try to make a picture. I don't have this. You see some sort of a pointer here? You see something moving?
Yes, you see your mouse.
Okay, yeah. So this is like a visualization of these 2 time series, X and Y. And the basic thing here is you try to predict the future of X. So the future sample of X, this one, n+1 on n+1, by the history of X. And this history of X and Y is denoted by KNL, commonly set to 1 for computational reasons, of course. But at ASML, we're of course interested in the strongest coupling. So we have the luxury to extend, to make K and L a little bit bigger. So what we do basically is shift X with respect to Y to and do this step 1 and 2, by the way, over a range of delays to find the maximum for the maximum information transfer from X to Y, or the other way around, from Y to X. And if the inclusion of Y's history improves the prediction of X's future, then Y is said to Wiener causes X. And you can repeat these steps 1 and 2 for all the n pairs. So n squared test is that you have to work out. And if you do that over a range of delays, then you can imagine that you run into computational costs. But the end result is a weighted adjacency matrix W. In this case, we're talking about 4 variables. The matrix is square by nature. 0 means there is no information transfer measured, so that implies causal independence, and non-zero entries denote transfers of information in bits, provided that you set this b, the log base to 2. You can choose another number like 3 or something, but then of course your unit of information will change into nets, for instance. So let's go to a simple example. Consider two binary time series, so not a continuous, but a binary time series for convenience and for simplicity. 22 samples for each. And I have to go one step back, by the way. These conditional probabilities can be transformed such that they can be transformed in terms of joint and marginal probabilities. So all you have to do is calculate all these joint and marginal probabilities, and you can do it by just shifting this F shape through the time series and then calculate all the different, let's say, permutations that you come across, and then calculate their probabilities. So you see, well, it's like 8 and then 8 and then these two marginals. It's a lot of work, and if you also add, if you do that over a range of delays, you run into computational costs. And this is for a binary series. So it's not hard to imagine what your cost would be if you take a continuous series, because in that case, then you chunk up the time series in more than 2 states. So if you repeat 1, 2, and 3 for, let's say, y to x, and you repeat it for x to y, then you get an end result of you get a net result of information transfer in bits. In this case, apparently, y adds 044 bits of predictability to x, and the other way around is a lot less, 011 bits of predictability to y. So we can conclude here that y is set to winner cos x. One more addition, yes. So here, for convenience, I took this case. Let's say you want to know how many times do I see this F shape filled with only ones? Well, this is clearly 5 times, which means that if you divide 5 times divided by 22, is 0.23. So your probability is apparently 0.23, and so you can do this calculation for all these other permutations. Well, next, so once you have your matrix, your weighted adjacency matrix, we can column normalize it to a probability matrix P or transition matrix. It's the same. This matrix describes the transition probabilities from one node to the other. And in that respect, we can look at how the PageRank is working, because this is quite similar. It's the same approach. You transform the the weighted adjacency matrix into a Markov chain. And you do that by, so all these values, this moment, these non-zero values, you can divide them by the column totals to get your P. So this 066 is a division of 0.82, sorry, by the column total. And you do that for every non-zero value, of course, and then you get your P. And the next step then is, because you want, we're looking for ranking. So now we go, so we did the measurements, the transfer from node to node in terms of bits, and now want to rank the nodes based on influence. So what we're trying to do here is to make sure that the network is connected. Because you can imagine that you might, while you measure pairwise between any two nodes, you can get one or two or more nodes dangling. And to keep a fixed scale to rank all the nodes, you need to guarantee that your matrix, your network is connected. And to guarantee that, you do this. It's exactly like they do in like the PageRank is working. You just add a all-ones matrix G, and then you choose a gamma to control for the probability of following an edge or jump to any other node. So you modify your transition matrix P to a matrix that is fully connected. And we call it matrix P strand. So in this matrix P strand, you can jump, so any node is reachable from any other node. And then from there, you can rank any node in the network. So, and then the last step is this P strand is a stochastic matrix, which means that it, by design, has a unique largest eigenvalue of lambda is 1. Which is pretty easy to solve with power iteration. It's you can solve this equation with power iteration and get the eigenvector with whose entries indicate each node's influence on the rest of the network. So not only on its direct neighbors, but also on the neighbors beyond the direct neighbors. And I really like this approach. It's very elegant. One remark I have to make: in Google's PageRank, it's about page significance based on incoming links. So important pages point to. So I inherit, if I am a page, so to say, I inherit importance by the pages that points towards me. In our case, in the ASML case, it's the other way around. I'm a node in a network, I inherit importance by my children. So I inherit importance from the children. not from my parents, but from my children. So that's a fundamental difference between Google's PageRank and the ranking mechanism that we use at ASML. And the consequence of that is that while information is flowing throughout the system in the direction of time, the importance is propagating backwards up to the in the reverse time direction. So that's a very important note to make here. For the rest, it's pretty much the same as the Google PageRank. So from here, I think I can go to some examples. This one is a part of what my most recent publication. Lorentz systems are very commonly used to validate causal invariance methods from data-based ones. And it's for me, it was very interesting to take not one Lorentz system, but take two and then join them together with a very complex interaction. It's squared, it's bidirectional, and it is delayed. So these are the equations. So it's a 6-dimensional model. I generated the time series here, and these are the typical butterflies, of course. And then I did a rolling window analysis by shifting a window of 2,000 data points. This is 150K. The whole time series is 150K data points of length. So I shifted like 50 times through this time series, and this network that you see here on the top, in the middle, is number 18. So this is number 18 out of 50 of these networks, and what you can clearly see, and that's the case in all 50 networks. There is no you won't have a problem discerning the Lorentz systems or Lorentz subsystems, I have to say, because now it's one system. Left is number 1 and right is the number 2. The strongest of the two is the right one. But that doesn't mean that so Y2 has a stronger coupling in the you can see that in the difference in the differential equations. The second one, you see that the coupling constant of Y2 is 2 times that of Y1. So of course, Lorentz system 2 is driving the Lorentz system 1, but not all the time. So from the 50 times, 10 times, I found it 10 times to reverse. So the driving and responding system, they switch 10 times, switch their role, by the way. But internally, the Y always was the driver, drives the other two. And I found the X variables to be the weakest of the 3 in both systems, all the times, all 50 times. And that is basically what these distributions on the right is saying. So the orange one and the gray one is the X variable. The orange one is X2, which is stronger than the gray one, which is from the Lorentz system 1, and so is the Y from Lorentz system 2 stronger than that of Lorentz system 1, and the same holds true for the C for the respective C variables in Lorentz system 2 and 1. So yes, Lorentz system 2 is stronger than drives Lorentz system 1, and internally the y variable drives both x and y, which is totally in agreement with the physics. The y in that atmospheric convection model from which this Lorentz system was derived, the y represents the up and down flow temperature difference, which they call the driver of the system, while x is the convective fluid flow, and c is the vertical temperature distribution. And what I found here with transfer entropy combined with eigencentrality is just the agreement with this well understood underlying physics of the system. And for me, the added value was to find the tipping points in driving and responding of those systems, that they change their role from time to time. And that is something that you can't, by no means, can't predict from the differential equations. So very nice, very interesting findings here. I found only one other analysis with transfer entropy on a Lorentz system, but it was only a single system, and the results were in agreement with what I have found for one system. But once again, I took two of these systems and connected them. One last remark: the delays I would expect from the differential equations would be 3 and 5. And what you see here, it's about 3 something and 2 7 something. These values vary over time, but they stay within a range of, let's say, from 2.5 to, I think, 6, which is quite remarkable over 50 of these things. Oh, okay. So the next one, actually, I had another case here, an ASML case, but that case was not allowed to share with the world outside ASML. So I took that out and replaced it by this case that I came across just by coincidentally, and but it turned out to be a very interesting case. Occupancy, I wasn't aware of that. Occupancy detection in buildings is a very active area of research. It's relevant because if you have information on occupancy, if you can measure that with great accuracy, then you can control it. Then you can control the energy consumption and a lot of other things. So occupancy-based control can save up to 40% of energy in buildings, for instance. So it's very relevant. What I notice is that most of this research is done with machine learning, and there was no exception here. So in this paper, I think it was a 2016 paper from Elsevier, they used linear discriminant analysis, classification and regression trees, random forest, and gradient booster machines, 4 of them, and then they assessed them on prediction accuracy of occupancy. Very nice. I plotted them here, time series. I have to say, I was lucky enough to have one of 2 best standard data sets for such a research. I was all that lucky. So time series from sensors, 4 variables, environmental variables, and then a camera to capture the ground truth, of course, for training. And the main conclusions from these authors was that the LDA, so linear discriminant analysis, turned out to be the best classifier in predicting the occupancy, not the level, but just so if 1 people was in, it detects it, if 2 people and so forth, but not how many people were in there in this building. But the accuracy was a mighty 97%, but all achieved with featured pairs. So temperature and light and carbon dioxide, and light and humidity or humidity ratio. So all the time, a pair of features instead of all the features. Because if you take all the features, then the accuracy tend to be lower. And the same holds true for the other classification models. And they explained that by saying that there was a good separation between the occupancy states, apparently. As you can see here, the occupancy is 1 or is 0, nothing in between. So I took this data and I feed it to my model, which tried to answer a different question, of course, not detection, but how are these environmental variables and occupancy, interacting with each other? And the second question is, which parameter, which feature is the most important in terms of network-wide influence? And there we go. So this weighted adjacency matrix here, you see these is normalized. What's it? So here you see the weighted adjacency matrix W, and it's normalized. So this 1 means 100%, and all the other values are of course lower. But you can think of it in terms of percentage. The same holds true for the relative importance. 1 means 100%. So occupancy is 100%. And as you can see, humidity, light, and so forth are significantly lower in their importance, so to speak, in their influence on the rest of the network. And that's exactly what and it's totally in agreement with what the machine learners has found. So occupancy is the most influential feature in the network. And what you can also see here is that so the width of the arrows is the magnitude of information transfer, The numbers along the arrows is the delay at which these maximum TE numbers were found. So what you can then see is that occupancy is so humidity and humidity ratio are very responsive. This is only one data point delay in their interaction with occupancy, which is different for temperature, different for light, and if you look any further down, then you see that humidity and CO2, for instance, has a very there's a very large delay, and also from humidity to temperature. They are the largest, but they are the strongest at the same time. The strongest coupling between these variables. So this triplet of variables, I would say, is non-obvious. I don't know what's going on here, but they're typical the comfort variables. Temperature, humidity, and CO2 are important in buildings where people stay all day. And I'm thinking of hidden impact of because there's no information in this paper on these things. Heating, ventilation, and air conditioning, open doors. They mentioned doors that were open or closed, but they didn't mention anything about plants, for instance, of which I know that if the temperature change, then the photosynthetic processes in plants change, and that might have influence on your CO2 level in the room. But there is no information in the paper on that. But very interesting to see how these three things interact with each other. So this is one cell with relatively large delays. But the humidity ratio and the humidity are pretty quick in their reaction on occupancy, and that is in full agreement with how it is described in the paper. So the nice thing of this this approach, I would say, as opposed to the machine learning one, is that you, at a glance, you have an overview of how all these variables are interacting with each other. And it also provides information on who is important and is the most important, and that may give you some useful information for control options. Then the last case, my one and only ASML case. This was a very tough one. I published on this in the recent paper. It was about diagnosing temperature, flow, and pressure instability. And the people who gave me this data of 400 parameters and 315 samples didn't give me one clue. They just gave me the data. And the only thing they told me is that the target was P27. I had to anonymize all this, so please forgive me for being cryptic, but that's the way it works at ASML. So all I knew was P27 is my target that I have to explain. And they also told me that the data was discretized, so the original data was continuous, but they discretized the data in a way that I think might be very interesting in future research. And I'm going to spend some time on that. But I processed the data. It took me just 30 minutes because of its binary nature. 30 minutes, including node ranking, and that gives me this Earth-like network, so to speak, of almost 1,200 links and 362 nodes. A very dense, of course, a very dense network, but this is a reduced network. So the real network is even more dense. I took out all the shortest paths here. So the original network is even more dense. But this algorithm is still able to find, so P27 is my target. And what I then do is find the network from the most important parameter, which is P0 in this case, and all paths leading to P72. I used a different application to find this network, a separate one. So this is the network that you end up with from this very dense network here. And this P0, I gave this result to the domain and service experts, and they told me you are just about right, because P0, yes, that was the problem. And it took them weeks to find that out, what the problem was, but it was a spot-on result. And they then gave me the service logbook, and after another week, they gave me the system event log. And the interesting thing here is that the event log that records error messages in our system follows the time. So you see here P23, sensor out of range, right? And then the following one is the one later in time, P16. So it just the messages are recorded in time order. But the service logbook is different. The service logbook here is an action that address this P23, but a following action later on, P1, is earlier let's say on the timeline of the system event log. So it's here. So P1 for the service logbook is pretty close to the root cause in the network that is reflected by the system event log. So this is a common thing, a common approach in Bayesian network inference, I have been told, and they call it diagnostic inference instead of, as opposed to causal inference, what just follows time. So causal inference follows time, and diagnostic inference follows the reverse order of time. So that was also a very interesting finding here. But the P0 was correct. So that was very nice. And they had 6 other cases of the same system, and they all had the same problem. So this, for me, this was just for that was just a proof of principle case, and I published about it. So for you who want to know some more about it, can just read the paper I just published at NDPI. So that brings me to some open questions, because yes, there are open questions, as promising as this method looks so far. You always deal with, you never know if the things that you observe is causal complete. So your data set is causal complete. So we're very interested in the question, how do you locate, at least identify or locate where the influence of the unobserved variables enters the system. Computational time is another one. It scales with the number of variables or with the resolution of your time series or quantization level, if you will. So if we want to ever get to, let's say, near real-time diagnostics at ASML, I think we have a long way to go. There are different options how to solve it. Brute power of computational power, or you make your algorithms cheaper, or you make the data cheaper. And that's that last one. That's one that I find quite interesting, given the last case that I just demonstrated, because that was continuous data that we discretized. And the result was spot on. So I think it might be worth to see if we can generally discretize continuous data within ASML, and see how that if that works, and if we can be, if it's accurate, if it's still accurate. So you're talking about how do you generally discretize your continuous time series while preserving causal information. So that's one big question. And another one is, I think, I talk a lot with Hans, who is here, about this. How do you define sameness or distance between causal graphs? Because if you have a causal graph and you do your analysis in this time frame and then shift and do this time frame again, while the system doesn't change, you don't expect the graphs to change. And if they do change, where's the limit? Where's the, what is the sameness? When are they different? How different should they look to say they're different, or they're still the same? So that's another big question here. Yes, I guess I'm through most of the. I think this was more or less the story. I have some references here. This paper on the methods we discussed today. This is the first one is my paper. The document that I used, the paper that I used for this occupancy analysis, David Zichtermans' work. I would encourage you to have a look there, because it's really new what he's doing. And these and the public software packages that I use, because all the software that I used is publicly available. The developer who developed this package, I go along with him now for 5 years. So we had a lengthy discussion on the combination of transfer entropy and graph theory, and he changed some of his changes in his software was because of our discussion, and I did some suggestions to change this and that because of the requirements that we have as ASML. A very nice guy to work with, and so this is the data set for the occupancy, and I would suggest, a good introduction to transfer entropy is that from Mr. Lichier, it's a green book. So that's about it. Are there any questions from your side?
Let's first thank the speaker. Thanks, Errol. There was quite some
Thanks.
lively chat. So yeah, who wants to pose the first question? You can raise your hand or just turn on your camera. Yeah, let's see. Who is the one? Yeah, Fiat, Luduc, go ahead. You're still muted.
It's very interesting presentation. I like it a lot. I just wonder about the first paper about the transfer entropy. So through what you explained, I think this method can only find the correlation, not the causal relationship. I assume that with the formula you provided, and you just provide two serial of error, just 1, 1, 1, 1, 1, yeah, and 1, 1, 1, 1. Then it's always have the maximum causal relationship. But that does not happen in the real life. For in the real life, the things happen together. They change the behavior together. They are correlated, but they are not the cause of one of the others. Yeah, so that is my point of view. Because I study causal learning more than 4 years, so I think this is a little bit. So I don't know if you really test with the system. For example, you do some experiment, then you have the factor A to cause the factor B, and then you try to predict that. Yeah, but not like taking, for example, what you had the temperature or whatever. They happen at the same time. They might not have a causal relationship. They might just have the correlation. So can you elaborate on this? For example, what you have also with Markov chain, for example, the principle of the method is Markov chain, and later with the hidden Markov chain, also with the long short-term memory and decoder network. Also, the last one is transformer. They all can only find the correlation, not the causes or the cause, the root of the problem.
Well, what I try to explain is that transfer entropy was designed to find to go beyond correlation, because correlation itself is a symmetric measure, right? Like you just mentioned, it's symmetric. So A associates with B, so you have behavior of A, you have behavior of B, or X and Y. And you can't tell who influenced who. Transfer entropy is by nature a asymmetric measure. So you have to decide, is it X that drives Y, or is it Y that drives X? And that is that future. So that's why it's predictive. So you try to predict a future sample of one series by the history of the other one, beyond the history of the signal that you try to predict.
Anyways, I think this can be a quite lengthy discussion. That, in view of time, I defer to the drinks afterwards. And maybe Rui, you can go ahead with your question.
Yeah. So let's see. Am I unmuted now? Yeah. So, well, I have essentially 2 questions / remarks, but I'll try to keep it very short. Right. One is that your ranking approach essentially disregards the fact that, well, you don't have the transfer entropy piece. You have pairwise estimates of the transfer entropies, especially in very high dimensional settings, right? Because these are not going to be exact. This is going to lead to errors. And did you account in any way? Did you take into account the fact that what you have is only estimates of the transfer entropy, not the actual values of the transfer entropy? So they are essentially noisy versions of the transfer entropy.
Well, I would always call them estimates. Yes. First and foremost, I'm talking about so measurement or estimating the transfer from one time series to the other. It's an estimate. So you it's a rate, right, over all samples. That's first and that's first and foremost.
But quality of this estimate plays an important role in your result. If the quality of the estimate is not very good, then you might hallucinate. Let's say a network that is very far from.
Well, there was one thing that I didn't mention, and that is, but it's in the paper that I just published, is that you do your measurement, your bivariate measurement, right, pairwise, and then you go to a that value. Your measurement should pass a significant test also. That's a very significant part of the test. So, and the test that I use is iterative amplitude adjustive Fourier transform. That means that so let's say I have X and Y.
Maybe in the interest of time we can skip the details for later. There's something there's something you take into account somewhere. Okay, that was my question. So that's fine. And the other remark, maybe I'll leave it for the drinks. Okay.
Yeah. So drinks can be found in the via Garda Town. I'm already there. We're on a beach. For people who have never used Garda Town, this is a kind of a funny online platform, but you can only see people and talk to people when you are together. So you can move with your avatar on this. In this case, it's an island, and if you're close together, then you see each other via your camera and you can talk to each other. But if you're not, maybe this is a good. It's a kind of adjacency matrix, like it's strongly connected. But if you're far away, then you don't see each other. So you can group together in several groups and have somewhat private conversations, at least conversation in your group. So I hope that you are all there. If you were smart enough to provide Anna with your address, hopefully you received a nice package. It's from a very local Turkish delicatessen shop in Enschede. I thought I like them, and I thought it would be good to support the local economy. So, anyways, if I don't see you in Garda Time, then have a great summer holiday, and we see each other after summer, hopefully also in physical meetings. So yeah. See you later.
Bye-bye. Okay. See you.
Thank you for the talk.
Yeah, thanks.
Yes, thanks indeed. Thanks again, Errol. It was interesting. And we can continue this causality versus correlational classical debate.
Okay. Long discussion.